Swayam Prabha. Digital India. Educated India.
Hello students, good afternoon. So, welcome to the comprehensive view of speech processing, and today's lecture is 28th in the series, and today we are going to discuss about the topic, a new topic. It's statistical pattern recognition. And before going to the today's topic, let us just very briefly review about the topics that we covered so far in just 2-3 minutes, then we move on to the current topic. So far in this comprehensive view of speech processing, so we started discussing about the introduction to speech processing. It means what is speech and what is speech processing and how humans process the speech. It means how humans produce the speech and how they perceive the speech, right. And afterwards we discussed about like acoustic phonetics of a speech signal. It means that the acoustic properties of various speech sounds. So, these things we discussed in view of time domain concepts and frequency domain representations, and we also discussed from a production perspective and a perception perspective. So, that way after covering the acoustic phonetics, we discussed about what are the various knowledge sources that are present in a speech. So, as we know that the speech carries the message, along with that there are lot of other information also it carries, such as speaker information, language information, emotions, and lot of other paralinguistic information that it carries. So, all that we have covered in the various knowledge sources present in speech. Then after covering this introductory part, we discussed about like how do we capture the speech, right, and then how do we represent the speech, or how do you store the speech, then how do we represent the speech signal. Then different ways of representing the speech signal, right, and that is a time domain representation, frequency domain representation, and so on. And along with that, actually we also discussed about like various types of the system representations for modeling the speech signal. So, it means the time domain representation, frequency domain representation, and jet transform representation, and the difference equations way of representing the system, and finally the pole zero representation of a system we had discussed. So, there are various ways we can able to represent the system and can model the speech, but each of them has its respective like advantages and disadvantages, and those things also we have discussed. And after covering these things, we discussed about how do we extract the relevant information from a speech signal, because as we mentioned that the speech carries the different types of informations. So, likewise from that, depending upon the given task, speech task, so how do we extract the relevant information from a speech signal, and in view of that we discussed about the features that can be directly extracted from a speech signal from time domain. And so, those are like energy related, energy profile, then the pitch profile, and the frequency related information. So, and autocorrelation features. So, these are the various time domain features we discussed, and after that we discussed about the frequency domain related features or frequency domain related information. In that we discussed about using the filtering approach or various types of filters like used for speech processing, speech coding, and speech recognition aspects. And after that we discussed about the linear prediction analysis, because we know that the speech signal contains the samples of a speech samples present in a speech signal, they are highly correlative. So, therefore, we can use the linear prediction analysis for modeling the speech, and in that aspect we discussed about using autocorrelation function or autocorrelation analysis for modeling the speech for in view of linear prediction analysis. So, the LP coefficients, Kepsum analysis, and all these various types of the features that can be extracted from a speech signal. And after that we discussed about a vector quantization, and here the concept of vector quantization can be used for representing the speech and as well as even for building the speech systems for limited domain applications, right. So, using vector quantization, we can able to represent the spectral vectors into a fixed code book and nothing but fixed symbols. So, that way you can use the vector quantization from the viewpoint of representation of a speech, and using a vector quantization we can able to compactly represent the speech signal, right. And the same vector quantization concept can be used for building the speech systems also, right. Suppose for example, if you want to build a speech system which is a limited domain like a number recognition system or digit recognition system. So, where using a vector quantization you can able to perform the task, you can able to carry out the task. And in the context of vector quantization, where if you want to build the speech systems or even for representation of a speech also, we need to perform a comparison between the two feature vectors are required, right. Because if we want to like code the speech, whatever the spectral vectors that are derived from a speech signal using a fast Fourier transform, and those feature vectors are represented by using a code vectors using a vector quantization. In that context, we need to compare the two spectral vectors, right. So, for comparison of two spectral vectors, in that context we discussed about the spectral distortion measures. So, how do we compare the two vectors? So, what kind of a distance measures or what kind of objective measures that are used for comparing the two spectral vectors. So, those also we have discussed. And then we are coming to the present topic, that is statistical pattern recognition, and it is a very important one in the context of building the speech systems. For building any speech systems, as we have known that we have some reference system or reference template or reference model, and with respect to that model we will try to compare the speech signal that is derived for the desired task. It may be for a speech recognition or for a speaker recognition, or it may be for language identification. So, whatever the task it may be, the input or the information that is available is from the speech signal. That means, from the speech signal we will extract the relevant feature vectors or relevant features and use those features, and we will try to like carry out the desired task, whether it may be as I mentioned like the speech recognition or speaker recognition or emotion recognition or whatever the other even for speech coding and so on. And here before going to the details of this statistical pattern recognition, I just want to like introduce I want to just mention the books that we are following or the content that whatever we have covered so far is mainly from this first textbook. It is like fundamentals of the speech recognition, and the authors of this book are Rabiner and Jong. This is the fundamentals of speech recognition. Most of the contents whatever we have covered so far, almost like 80% of the contents are covered from this textbook, right. And the present topic whatever we are discussing, that is statistical pattern recognition, that is the fundamentals of that, or just very brief overview of that we are covering here. And that for this we are following this particular textbook, Neural Networks for Pattern Recognition, and the author of this book is Christopher M. Bishop. And in this textbook, the first two chapters will try to cover for giving you a brief overview of the statistical pattern recognition. And so, under this statistical pattern recognition, we will try to cover the following topics at a broader perspective. And so, here the thing we say that the topic is statistical pattern recognition, means we know that here in the context of speech, for performing various speech tasks, we will try to match the patterns. That means, here in a speech signal, for example, suppose if you try to analyze the task related to speech recognition. So, the speech means it contains the message, where the message will be in the form of like a text, whatever we have seen, the sequence of words, and that words are actually spoken are nothing but the sequence of sound units. So, it means that the speech signal is nothing but it contains the sequence of sound units. The speech recognition is nothing but from a given speech signal we need to identify or we need to recognize the sound units, the sequence of sound units. So, once the sequence of sound units are recognized or detected, identified, and from that later on, by knowing the language, we can able to derive the words from that. By taking a particular sequence of sounds, we know that yeah, this is a particular word. Likewise, by using the language models later on, from the sequence of sounds, you can able to derive the text that forms a message. So, in the context of speech recognition, the basic task is that given the speech signal, and we need to find out what are the sequence of sounds the particular signal carries, and each signal, each sound unit, it has its specific pattern in the context of time domain representation or a frequency domain representation and all, like a sequence of feature vectors that represents a particular sound unit and all. So, therefore, from a given speech signal, we will extract a sequence of feature vectors and we will try to match this particular sequence of feature vectors with respect to different sound units, because a priori we do not know that what sound unit we have spoken and all. We need to detect that, we need to recognize that, we need to identify that. So, therefore, we know that in any language there will be like around 40 sound units will be there. So, somehow by using this statistical pattern recognition techniques, modeling techniques, we will try to model each sound unit like with a sufficient number of examples. So, for example, in the case of speech recognition task, we have like 40 sound units. For every sound unit, we will develop a model, we develop a statistical model, and then for in the recognition phase or in the testing phase. So, given a speech signal, we need to detect or we need to identify what are the sound units that particular speech signal carries. So, for that we will extract feature vectors, and those feature vectors will be tested against all these 40 models. It is nothing but matching the pattern kind of a thing. So, whichever the pattern, whichever the model best matches, and then we will hypothesize that these particular sequence of feature vectors or this particular speech signal carries this particular sound unit. So, that is the overall task at a very gross level, and towards that for going to the details of that, before that we will try to give some very brief introductory about like what is pattern recognition, how do we perform that, right, and then how do we apply that in the context of a speech signal. So, in view of that, in this first 1 or 2 lectures, we will try to give very broader introduction related to a pattern recognition, and here we are saying it is a statistical pattern recognition, because here the signals that we are dealing here is the speech signals. The speech signals are not deterministic, they are quasi stationary. It means there is certain inherent variability will be present in the speech signal. So, therefore, when you are extracting the features, you do not expect the features are deterministic. There will be some kind of a randomness or some kind of inherent variability that exists in the features. So, therefore, the feature, when you are extracting the features or when you are building the models or when you are performing the matching task or recognition task everywhere. So, we will build the models or we will use it the statistical framework, because as I mentioned that it contains some inherent variability. To accommodate that, we call this we will view this pattern recognition as not a deterministic one, in other way it is like statistical or in a probabilistic framework. And coming to here, these are the various topics that we will cover in this particular lecture and in the coming lecture also, like a pattern classification. What is pattern classification? Then what is pre-processing, feature extraction, curves of dimensionality. So, there are various topics that are listed over here, and we will see one by one in a very briefly in a very simple way which you can able to understand, so that later on these can be used for developing a speech, for developing the models in the context of speech for performing various tasks, right. So, coming to the pattern classification or pattern recognition. So, as I have given the example that in case of speech recognition, here the pattern classification is nothing but from the speech signal we will extract features and use those features, and we had to classify those features, sequence of features, as which of the sound unit this particular sequence of feature vectors corresponds to, right. And for making the things to be simpler, here we considered the pattern classification problem for a very simple problem for very clear understanding. We consider that here the problem we are considering here is the handwritten character recognition. That means all of you are aware of that the cursive script like which we used to write using with a pen and paper. When you write the text, it's known to be cursive text or cursive script, where humans write like whatever the language it is. It's known to be like a cursive script, or it's like a handwritten text, right. Here the problem is that we are trying to perform the handwritten text recognition using a machine in an automatic way. Like, so as a human, when you see this handwritten text, we can able to know that actually what is this. So we can able to clearly read out this is a pattern classification example, character recognition, A, B and so on, all of them we can able to do that. But here the task is that given this image, the machine has to perform this task. The machine has to recognize this text and derive the corresponding text out of it, right. And as I have seen, similar to the speech signal, in the handwritten characters also there is a lot of variability used to be there. When you try to write A, for example, you cannot write the A the same thing exactly the similar way in the next instance. There will be some kind of a variability will be there, but as a humans we get used to that and we are okay with that. Even though we have a variability, we do not have any difficulty or we can have any issue at all, right. But in the context of machine recognition, we have a problem. How do we accommodate that variability and so on, right. So here, to perform a character recognition, instead of strictly speaking, this character recognition problem is it's a 26 class problem, because if you consider the English as a language, there are 26 alphabets. So whatever you write in English, if you want to recognize that, right, so you need to recognize all the characters. So therefore, if you view this problem as a pattern classification, then the number of different classes in this problem will be 26, because there are 26 alphabets and your handwritten characters or your cursive script contains 26 characters, and also therefore we need to recognize each of the character. But for the sake of simplicity, we are considering only the two characters. We consider the two characters. So therefore, we reduce the problem complexity to 26 to 2. That means we are assuming that we had to perform a character recognition, and the problem this character recognition, we consider only two characters A and B. We consider only two characters A and B, right. It means that all the time whatever you want to recognize or whatever the character you are given, it is either A or B, and your machine has to identify that whether it is A or B. And here in this case, here the input will be in the form of image. Input will be in the form of image. That means this is the way, like it means we have a cursive script and we take a snapshot of that, and then we will like segment that at a character level, and each segment will be given to the machine, and the machine has to identify that whether it is a character A or B, right. So here it is a two class problem. It is a two class. That means we reduce the complexity, like for giving more clarity. So instead of 26 class problem, we are assuming that our character recognition problem contains only two classes, and those two classes are A or B, A and B, and the input will be the image, and the image size of the image will be like a 256 cross 256. That means this image size will be 256 pixels in the height direction and 256 pixels in the width. So it is a 256 by 256 pixels, that was the image, and where in that the character A contains, and each pixel contains a gray value. So to represent the gray value, gray value means there are about 256 gray values used to be there, like from white to the black. So for representing these 256 gray values, we require 8 bits. So therefore, for representing each image of this character, we need 256 cross 256 cross 8 bits, right. So with this, each bit is a binary bit, it takes 1 or 0. So therefore, the total overall possible images will be, for this particular size resolution will be 2 power 8 into 256 into 256, right, because the number of pixels will be 256 cross 256 where each image contains, and the number of gray levels equals to 256. So therefore, that can be represented by using 8 bits. So therefore, if you consider all possible images by taking all possible gray values, right. So the number of images, possible images will be this one, this is the order, like a 2 power in the exponential 8 into 256 into 256, this is approximately equal to 10 power 158,000 or 1,58,000. It means that the possible images that are required, that are used, that are possible will be this is the order. This is very huge number of images and all. That means here if we want to perform the recognition using a very naive way, that means by matching pixel by pixel level matching, right. So, we need to have, these are the possible images that used to be there, and with that we had to match, then the recognition can be possible. But having this many images like a 10 power 158,000 will be very huge order, and it is practically impossible. We cannot perform a recognition task like this. So, here for performing recognition task, what you are using? You are taking directly the raw pixel values, like, because we have a image size equals to 256 by 256, and each pixel will take 256 values, one of the 256 values. So, therefore, 8 bits are used for representing each pixel. So, with that the total possible images will be, this is the order 10 power 158,000. So, we cannot perform the recognition task with this many templates, right, with this many reference images we cannot perform it. So, therefore, it is not simply not possible. So, the way out is that if you can able to perform, if you can able to derive some features, like by knowing the recognition problem, by knowing the problem, then by knowing the domain knowledge, we know that here the task is to, it is a just 2 class problem, and in this 2 class, one of the class contains the character A of this particular shape, and other class contains the character B, where the gross shape of this character will be like this. And by knowing these characters shape and other characteristics, we can able to do a much better job compared to this kind of raw values, comparing the raw pixel values and all. But comparing raw pixel values, it is not possible simply, because this many images means it is very huge, you cannot do it, it is not simply not possible. So, the way out is that by having a domain knowledge, we can able to extract some relevant features from these images and use those features for discriminating the images, like, because all the way we know that the images are only 2 types, one is holding the character A and other one is holding the character B, right. And by knowing the character A here, as a human I can see that in a character A, like the height of this character A is slightly smaller than the width of the character, the width of this character, whereas in case of B it is other way, the height of this character is much larger compared to the width of the character. Suppose this is the width, because you can see the width we have like a 4 boxes, whereas the height will be that there are 8 boxes, whereas here the height will be about 5 boxes, the width will be about 6 boxes and all, it is other way. So, that way by knowing this knowledge, one can able to say that you can able to derive the feature from this particular image, like from this particular image, like height by width as a feature, for example. So, use that feature and you can able to discriminate the images, either it is a class A, either it is a character A or a character B, right. If you look at A, for example, handwritten character A, so this is the width and this is the height, whereas in case of B, this is the width and this is the height, right. So, in case of B, the height by width is higher, and in case of A, the height by width is lower and all. So, by using that knowledge, one can able to discriminate the images using by extracting the features. So, here the question is how do you extract the feature? So, that by using some image processing techniques, we can able to, first of all in the image we have to locate where the A will be, and after that what is the height of the A and what is the width of the A, it is nothing but in terms of number of pixels, and then you can able to find out, you can able to derive the feature like height by width, like that, you can do that. So, once we have this one, then you can able to discriminate very effectively, right. So, that way like this is known to be feature extraction, and this is also known to be pre-processing. That means, instead of using the images raw pixels directly for comparison for recognition purpose, we can do some pre-processing. It is nothing but convert the raw data into the features, convert the raw data into features. It means the raw data is nothing but the pixels, 256 by 256 pixels, each pixel have 8 bits, and from that somehow if you can able to derive the feature, right, and then use those features for discrimination task, for a classification task. Okay. And here when you are using these features, right. So, the way how do we can use the feature, like, so that means for example here from this and another thing, using the features there are some certain advantages, because by using this feature, so even though the character A maybe here in this case it is around the middle of the image, and sometimes the A may be here in this corner with a smaller size, and here the B may be somewhere here in this corner or in the here bottom here, right. So if you go by raw pixel values and all, there will be a problem, whereas if you choose this feature, even though the size of the A may be either larger or small, by taking this height by width ratio, we do not have any issue at all, right. Similarly, suppose the A may be placed at this center or at here position, at any position in the image also. If you can able to identify the location of A, we can detect the width and height, and from that you can able to calculate the ratio of height by width, and from that you can able to derive the feature. And so that way I can say that these feature extraction or these features are like they are robust. What it means is that they are translation invariant. There are translation, that means whether the A may be at the center or A may be at the at the top of the image, at the the top side of the image or bottom side or this lateral side or anywhere in the corners. If you place A alphabet A at anywhere, once you identify the A where it is, and from that if you extract the feature, then it remains same, you do not have any issue at all. It means that the A can be located anywhere in the image, we do not have any issue at all. Whereas similarly the size of the A also, the A may be this much bigger or A may be smaller also. If you keep A smaller also, because since you are taking the ratio, so it does not matter, the feature remains same. So therefore what I am saying is that by using this feature extraction, these features are translation invariant, that means the location invariant, wherever the A can be located, no issue at all, and the size of the A also, whether the A may be larger or smaller, no issue at all. So that way the feature extraction not only add the advantages of at the time of recognition, it also takes care of certain robust features like adding translation invariance and scale invariance. All these things will be inherently takes care by the feature extraction, and with this example we can able to it will be clear to you. And here now let us see, like for example after knowing that by feature, intuitively you can say that by using this feature you can able to discriminate. But how do you perform this automatically by a machine? How do you perform this automatically by machine? So for doing this here, when you take this A, as I mentioned that this is a character written by a human, so there will be certain variability used to be there, like. So therefore when you calculate this height by width ratio also, the height by width also, it is not constant all the time, it will be, there will be slight variance used to be there. So we need to model that particular variance or variability, and then that model can be used for recognition at the time of recognition, For that what we do? So we will take some sufficient number of handwritten characters of A and handwritten characters of B. For example, if we take some 100 examples of A and 100 examples of B, and for each image we will derive this feature like height by width ratio. Height and width will be calculated and the ratio will be calculated, we will get one value per image, like that is the feature. So that way for all 100 images of A we will derive that feature, and we will find the distribution of that, It means that if we calculate height by width, that x1, and that x1 will have certain range, right. If we compute for 100 images, we will give 100 x1 values, and if you see all these 100 x1 values, there will be some minimum value, some maximum value, and the other values are false in between that. So if you plot the distribution, then we will come to know that how these height by width ratio is distributed in the range, given range. Likewise for a B also we can able to do that. So in principle, intuitively what we can observe here is that by plotting a distribution of x1 for A, you can able to see that the distribution will be towards lower side, because the height by width of A will be lower, slightly less value compared to B. So therefore if you plot a distribution of for height by width or x1 feature for character A from the 100 examples, you can able to see that the distribution will be towards the lower side, and whereas for a B towards the higher side and all, right. And that if you can able to see here. So here this particular plot is nothing but distribution of class 1 and class 2. Here the class 1 is nothing but distribution of that x1 feature, that is height by width ratio, that is derived from the 100 examples of character A, right. And the C2 is nothing but the distribution of 100 examples of this one B, character B. Like from each image we will derive the x1 value, and all those 100 x1 values, if we plot it as a distribution, you can able to see the distribution of C1 is nothing but corresponds to the distribution of 100 x1 values corresponds to A, and here the dotted distribution, this corresponds to the 100 x1 values corresponds to B. So, this is C1 and C2. So, that way you can able to plot the distribution, and from this it is clear that the lower values are, you can say that they are definitely corresponds to A, and here the higher values are, they are definitely they corresponds to B, and there is certain region where both A and B exists. There is certain region where both A and B exists. That means here for this particular x1 value, there are some examples of A also available and some examples of B also available. So, therefore, this particular region, the overlap region, where we have a confusion in the classification. Otherwise, here at the beginning we do not have any ambiguity at all, and at higher side also we do not have any ambiguity at all, but in between we have ambiguity. There may be some examples whose value will be overlapped with the B also. So, therefore, here we have some overlapping will be there, and in this overlapping area that leads to the misclassification and all, that leads to misclassification. So, here you can see what we have done. Here pre-processing we have done, it means that from raw values we extracted the features, and it is nothing but raw values are nothing but pixel values, and the feature is nothing but height by width ratio x1. And when you plot this distribution with respect to each class, what we observed is that there is at certain in some region the features are overlapped, that we observed here. So, because of this the misclassification will take place, right, and to get the minimal misclassification, what we can do is that we have to keep a threshold. That means we need to, because from a mission point of view, we will have, that means from the input image we will extract this height by width ratio, we will get a x1, and based on x1 value we have to decide, we have to classify that whether the given image is either A or B, right. For that we need to use some threshold value, right, and here we will choose the threshold as this one, the cross section of these two curves, whichever is the value. If you take this threshold, that gives you the minimal error and all. Otherwise, if you take a threshold towards lower side, then the more number of B's will be misclassified. Otherwise, if you take the threshold as slightly higher side, then the more number of A's are the misclassified and all. So, that way you have a problem. So, therefore, you will get if you want to have a minimum error. So, that means wherever these two distributions are crosses, so at this the cross point of these two distributions can be taken as the threshold for deciding or for a classification task. Okay. Next, as we have seen that if you use one feature, you have a problem. That means we have overlapping of features. So, then how do we overcome the situation? So, one way to overcome this situation is that this overlapping of features can be reduced, or can able to take care of it by increasing the number of features. Instead of having only one feature, right, for representing the image, instead if you use the more number of features, right, because since we have only one feature, it means that we have only one axis or we have only single scalar. So, with that we have to decide. Suppose instead if you have more number of features, suppose if you add one more feature for example, then you see that the space will be increased. That means now you have a 2D space, you have a plane. Earlier we have only one line, on that all the points will be lies on that, and we have a overlapping. So, therefore, we have a decision will be difficult, right. We have some misclassifications can take place. Suppose if you increase the dimension of a feature, or if you add one more feature, additional features, right, instead of single feature if you add one more feature, then if you see the plots, the feature values, because here if you see each of this value corresponds to x1 and x2, right. Suppose this cross corresponds to, it has this much of x1 value and this much of x2 value. So, likewise for every point here corresponds to two features, both x1 and x2. So, that way if you plot these points, the features in this feature space, you can able to see here So all these crosses and all, they are at one side, and all these circles, they are at one side, and there is very few points are misclassified, there are here in this case, right. And here these two patterns, or these two feature, these two classes, you can able to separate it out using a line. Using a line, you can able to separate it out, right. You can able to line, by using a line you can able to separate it out. So what from this what we can infer is that, so if you increase the number of features, then the discrimination will be better, then the misclassification, that the overlapping of features will be reduced, because the space will be increased compared to one dimension. If you make it as two dimension, then instead of line, now we have a plane, right, we have a 2D plane. Suppose if you add one more dimension, now we have a 3D space. Like if you add one more, you have 4 dimensional, we have much more. So likewise, as you increase the number of features, the space to represent the features will be increased. So with that you can able to discriminate them very effectively. That was the idea to overcome the to reduce the misclassification and all. So you can see that when they increase the number of features, so it will reduce the misclassification, that you can able to observe from here and all, that you can able to observe from here, right. But as you keep on increasing the features, right, the misclassification will be come down to some extent, but at the same time, as you keep on increasing the features, after certain limit, the classification performance again go down, the classification performance again start reducing and all. And this problem is known to be curse of dimensionality. Curse of dimensionality, it means that initially what we observed is that with using very fewer number of features, those features will be overlapped, and that leads to misclassification. So to provide best discrimination, the better discrimination, we are increasing the features. As you increase the number of features and all, the dimensionality of the feature vector increases. So with that it expects more number of examples, or more number of the data, and if you do not have sufficient data, then that leads to again the misclassification, leads to again the recognition performance will again come down. It is known to be the problem that arises due to the high dimensionality is known to be curse of dimensionality. That means as you increase the dimensionality after a certain stage, the recognition performance will go down due to lack of sufficient data. We will see that. Yeah, this is the idea of curse of dimensionality. It means that for example, here if you look at here, here if you look at here, for example, earlier we have x1, right, we have only one dimension, right, and so that means we have x1 value, that is height by width ratio, and it has some lower value, higher value, and then if you divide that into different intervals, for example, and with that we plotted a histogram. So when you split that into different intervals, for example, if you divide this feature x1 into m bins or m intervals, right, and to have a classification task, at least each interval should have at least one example, right. Otherwise, suppose if the intervals, if you make the intervals are so very close part, and then if you make the several intervals, and if the data is not sufficient, there are certain intervals where there is no example at all, right, and there we have a problem. That at that time we do not know in that particular interval, if the test example falls into it, we cannot recognize, we do not say that, we do not comment on that whether it is a class 1 or class 2, right. So here if you have one dimension, and if you split that like the range of this feature into m bins, we need at least the minimum m examples are required to accommodate all these bins, all these intervals and all. Like for example, as I mentioned that if you have only one dimension, the problem is that the overlapping of features and misclassification. So that is the reason that we are increasing the features. Suppose instead of one feature, if we make it as two features, x1 and x2 for example, and now if you increase the features from x1 to x2, for example, two features. So for each of them you see that x1 requires m intervals, and again x2 requires m intervals, right, and then the space that is provided by x1 and x2 together requires m square blocks, and now if you want to use this x1 and x2 features for representing the feature, so here the number of blocks, or number of, you can say that here the blocks will be m square block. Each block should have the training example. Then only we can say that based on that we will say that yeah, this particular block contains the class 1, this is contains class 2, something like that. And if you do not have sufficient number of examples, then there are certain blocks where they do not have any data at all. So at that time we do not comment at all. we do not comment, we do not have any idea about if the test example falls into that, then we cannot decide, we cannot comment on that whether that particular example belongs to class A or class B, right. So, this is the case scenario for 2 dimensions or contains the 2 different features. Suppose if you increase the features further, for example, if you look at here, it is a 3 dimensions. If you increase the features like using 3 different features, you see that the number of bins that are required will be along x side you have m bins, along y side you have m bins, and along z side you have another m bins. So, the number of bins that are required or the number of blocks that are required will be m cube. So, that way as you increase the dimension like a d, the number of blocks or number of cells that are required will be m power d, that is m exponential d. Like if the d equals to 20 and if you make m equals to for example 10, then in that case the number of examples that are required will be minimum 10 power 20, like the number of cells, each cell should contain at least one example. So, what we inferred from this is that as you increase the features, yes, the discrimination will increase, but at the same time as you increase the features keep on like after certain limit, if you do not have sufficient data to model that particular distribution, then that leads to a problems, that leads to be like that misclassification and all. So, this problem is known to be like the curse of dimensionality, because as the dimensionality increases, right, the volume that is need to be covered by the data is increases exponentially for every dimension. Like you can see here m power d, with the d equals to 1, only one dimension, only one feature, there are only m bins are there. If d equals to 2, m square, if d equals to 3, m cube. So, likewise as the d increases, the volume that need to be filled with the data has to be increased exponentially, but that leads to problems. So, that is known to be curse of dimensionality, right. So, it means that at a lower level as you increase the features, the discrimination will be increased and classification accuracy will be increased, but that is up to certain limit. After that, if you do not have sufficient data and if you increase the dimensionality of features, then that leads to again misclassification. That means the classification accuracy again will be reduced. That is known to be the curse of dimensionality, because this is the curse, this is lowering the performance because of increasing the dimensionality. So, yeah, next at this point actually here we are introducing one more term known to be regression. So far we discussed about classification. Classification means it is very clear to us as of now, because we are given examples like in case of speech recognition, the classification is nothing but given the speech signal and you have to decide that what sound unit it carries. Like we know that there are 40 sounds, so therefore we need to build a 40 class problem or 40 a system having 40 classes, and then we have to decide which class or which sound unit this particular speech signal carries. Likewise, in case of cursive script recognition, so if you take an image and from that image we need to decide that which alphabet it contains, or suppose if you include the number also along with the 26, another 10 numbers will be there 0 to 9. So, altogether will be 36, it is a 36 class problem. So, likewise we know that a classification problem is nothing but given the input. So, we need to decide that the input belongs to which of the outcoming or which of the given finite number of classes and all, right. In case of speech recognition, which sound it is. In case of character recognition problem, which character it belongs to, right. So, that way if you see our real time examples, we can able to formulate the problem accordingly. For example, if you take a speech signal and we know that the speech signal may be one of these 10 languages, that means it is a 10 class problem. And likewise speaker recognition, we know that in a room it contains only some 30 speakers, then it is nothing but it is a speaker recognition problem which is contains the 30 classes likewise. So, that way here we are introducing one more term known to be regression. So, here both the classification and regression at some extent at some context they both mean the same. It means that both will come under a problem of function approximation. That means both can be solved by using a function approximation, right. And so, it means that actual function approximation, suppose we have some system where it has some underlying function, the characteristic of the system is built by some underlying function, and we need to capture the behavior of the function, so that we can able to come to know about what is the behavior, what are its characteristics and so on. So, with that we can able to provide an output belongs to the input, right. So, both the classification regression will come under the problem of function approximation, but how they differ are, in case of classification task, the outcome will be discrete classes. The outcome will be finite number of discrete classes. Given an example, speech recognition, it has a 40 classes, right, where each phoneme or each sound unit as a class, whereas in case of character recognition problem, 26 classes where each alphabet as a class. Whereas in case of regression, the outcome of a classification, outcome of this system, outcome of this will be expected to be not a discrete, it is a continuous one. The outcome will be continuous one. So, most of the prediction tasks will be come under the regression problem, come under the regression task. For example, you have a stock price prediction. It means that we know that our stock market for different stocks under the prices will vary, and suppose we want to predict the price of the current price of a particular stock of today. For that, if you know the history of that stock price for a last 1 month or last 2 years or 3 years, from the previous history you can able to predict that particular stock's present price, and the price will be vary, it is a continuous one, it may be 10 rupees 20 paise, or it may be 10 rupees like 52 paise, something like that. So, it takes a continuous value, right. Similarly, in case of weather prediction also, the weather prediction also you have a lot of other variables will be there, like temperature and whatever, the cloudiness or like precipitation, humidity, so many other things. By taking all these parametric values into account, we can able to predict the weather with certain degree of rain or whatever and all. So, therefore, the outcome